Hello everyone, my name is Pratyush Karna and I welcome you all to this presentation of my final IBM Capstone project for the Advanced Data Science course. My project is titled as Forecasting the Highest Stock Price Over Time with Advanced Machine Learning. So let's get started. So the agenda for the first presentation is defining the business use case, the data set I've used, the solution I've implemented, the technology stack for my implemented solution, followed by a small demonstration of my final data product. So defining the business use case. So the end goal is to perform time series analysis on stock market data set and predict the target, that is the average daily highest stock price of an RIC for the upcoming 6 months. So just to let you know, an RIC is a ticker that identifies a company in any stock market data set, and throughout this process also determine what factors impact the highest stock price of an RIC the most, and thereby assist buyers and investors in their decision making process through actionable insights via the solution that I'll be building. And at the end, deploy the use case as a user friendly product that can be availed and accessed by end users from different backgrounds, from different teams of an organization across the spectrum. Define the data set. So the data set, it's an open source Kaggle data set. It comprises of two files. First one is historical stock price data. It has daily opening, closing, highest stock price and the daily trading volume for an RIC ticker over time from January 2019 to September 2023, basically 4 to 5 years of data. And the second one is more of a referential data set, which is the sector data. It has the sector-based information associated with each RIC ticker, such as the company name, the industry name, what economic and business sector it belongs to, activity names, and so on. So this is an overview of the solution that I have built. So the data product lifecycle consists of three major pipeline stages. The first is exploratory analysis, in which I perform data quality checks, like finding the null value, how many null values are there in each feature or column, finding the statistical summary, the dimension of the data set. Then I perform a univariate analysis. In univariate analysis, I basically find the frequency distribution and outliers of each feature. The multivariate analysis, in which I find the behavioral trends, correlations among two or more variables, and based on these analyses I come up with the recommendations for the next phase of ETL, which is the extract, transform, and load. This phase comprises of two parts. The first is data cleansing and the second one is feature engineering. So in data cleansing, based on the EDA recommendations, I clean the data, such as dropping the duplicate records, handling the nulls, renaming columns accordingly, and applying necessary transformations, aggregations, etc. And the second part is feature engineering, in which I try to find the features that can have the most information or that impact our target variable the most, and how to use them in our next phase, which is the model building. This is the most important part, in which I have built two models. The first one is a machine learning model, which is the random forest regressor, and the second one is the LSTM recurrent neural network from the deep learning stack. So what I want to basically do is implement one model from the machine learning stack, one from the deep learning stack, compare their performances, and deploy the best performing model out of the two as a Flask based web application. So here is the underlying technology stack for my project. So I've used PySpark as the underlying data structure. So because PySpark is a very powerful library that allows you to run your data manipulation on multiple compute nodes, it's very powerful, very fast, especially for large data sets like the one that I've been using. It's all in Python. Then NumPy, Apache Spark SQL for creating table views, running SQL queries on them, and then Seaborn and Matplotlib for intermediate data visualizations. And all of this coding has been done in Jupyter Notebooks. I'll be also showing my Jupyter Notebooks in between throughout this presentation. And finally, for the web service, I've used Flask. So Flask is a library in Python for web development, for building the backend and the web services. And for the front end, I've used HTML, CSS, JavaScript, and a library called Chart.js. It's a very interactive, lightweight library that helps in building interactive visualizations on our web pages. So here is a small demo of my final data product. As you can see, this is a web application. It has a form in which we give the ticker, RIC ticker, as the form input, and on submitting this, this is what we'll get the next 6-month forecasts for this particular ticker that I just input in the form, the sector based information like the company name, the economic sector name, business sector name, etc., and a chart.js line chart. So in this line chart you can see what the stock price is, the daily highest average daily highest stock price of this particular RIC will be over the next 6 months. So this is how it's deployed, a data product. Of course, there can be multiple improvements, more improvements can be made on this, but that is more on the front end aspect. But yeah, this is the underlying deployment idea behind my use case. Now, this is the second part of my presentation for my data science peers, in which I'll be explaining my architectural choices, my data quality assessment results, outliers and frequency distribution, how did I pre-process the data, feature engineering, my model algorithm for both random forest and LSTM, the performance indicators, and my final conclusions and summaries. So for the data architecture, so for my architectural choices, so for the data sources, I told you that I have 2 CSV files that were directly taken from Kaggle. For data integration, like applying the transformations, aggregations, and other manipulation stuff, I've used PySpark and Apache Spark SQL. For the exploratory analysis, data discovery, again I have used for functions of PySpark data frames. PySpark has a lot of powerful functions that allows you to explore and analyze the data, along with NumPy and Seaborn and Matplotlib. Seaborn and Matplotlib, as I mentioned, were mostly used for intermediate data visualizations, and for actionable insights, Seaborn and Matplotlib mostly on a programming end, and Chart.js for the actionable insights on the end user end, which you just saw recently. And for the final data product, I've used PySpark because I first initialize a Spark instance in my Flask application, because the ticker that we'll be using is located in a PySpark data frame, then Flask for the web service, the backend web service, and then HTML, CSS, JavaScript, and Chart.js for the front end. So these are my data quality assessment results. So the main stock market data set, it had around more than 500k records distributed along 6 features. These 6 features are basically the instrument or the RIC name, the date, highest price, closing price, opening price, and the daily trading volume of that RIC. So on performing the null check, you can see that these are the number of nulls that were found in each column, and the number of duplicates were more than 15,000. So all of this was handled in the data cleansing and pre-processing. But before we go to the data pre-processing, first I would like to shed light on the outliers and frequency distribution. So you can see this is how the distribution of our target is like. So all the 3 variables, like the daily highest stock price, opening price, closing price, and volume, follow a somewhat similar distribution. So I'll show this in my Jupyter notebook as well. Here, if you can see, this is the highest price, which is also in the presentation, the opening price, the closing price, and the daily trading volume. So as you can see that this is neither normally distributed nor it is free of outliers. On the contrary, it is very skewed. The distribution is very skewed, and it is full of outliers. There are a lot of outliers in this particular data set. So based on that, what we can do, we cannot impute the nulls by the mean, because mean assumes that the data is normally distributed and is also outlier sensitive. But at the same time, I cannot just directly remove the null values, because that might lead to loss of information. And we cannot impute with the mode, because mode is mostly used for imputation for categorical variables. So the most prudent choice over here was imputing with the median. So first what I do is I remove all the nulls in the date column. So basically any RIC that does not have any record or a row that does not have a date is a noise. I remove those, and from that what I do is I impute with the median. So this is better explained in the data pre-processing. So first remove all the null records with no date. These are basically noisy data that need to be removed. Then from the date extract the year and month, because based on the year and month we'll be aggregating our data. Then impute the highest opening, closing and the daily trading volume with the median just suggested previously, and aggregate them over the RIC, year and month. So shedding light on this, so this is how it has been aggregated. Here I'll yes, here if you can see, yeah, so I aggregate them over the instrument is basically RIC, year and the month, and I find the average highest price, closing price, opening price, the average volume and the total volume for that day. And I also create an additional feature called average daily return, because this is derived from the opening and closing price average feature. So average daily return is basically the difference between the opening and closing price, which could be helpful in our feature selection. So that is what I'll be highlighting in this part. So the feature engineering part, for feature engineering I used two concepts. First is the correlation from the multivariate analysis, and second is calculating the feature importances. So as you can see over here, the average closing price and the average opening price, they have the highest feature importance towards our target of the daily average daily high prices. And not just they have a very high importance, they also have a very strong correlation. So we can say that these two impact the highest price the most, and quantitatively speaking they contribute to about 88% of the feature importance. The daily volume is very low on both correlation and the feature importance, so it won't be wise to use them in our feature set. Regarding the average daily return, so it is optional, so we can use them, like for, because although it has a very low feature importance, but it is a derived feature, and that too derived from two such features that have a very high feature importance. So they might add more information, but that depends upon the testing results of the model. So coming to the next part of my model algorithm, so the first few parts are very much similar, because for both random forest and LSTM what we need to do is find the feature vectors, scale the features. Now scaling is optional, so because we can directly use the feature vectors, but if they're not on the same scale then we need to scale them. It depends, it's optional, you can use, depends upon how your model performs, like scaled between scaled and unscaled. Then I define the training and the test data. So I'll explain the next part shortly, but before this I would like to shed light on my training and testing logic, like how did I define the training and test data. So usually what we do is we use a train test split like 70 to 30, 80% to 20%, etc. But for my use case I have used a very unconventional method of train test split. What I've done is I've defined my training set as historical data from January 2019 to September 2022, and my test data from October 2022 to September 2023. The reason being I wanted to include the time series aspects in my training and testing data. I wanted to know whether, like, if I train on an historical data, will it work on a test data of the future? So that is my rationale behind this train test split. And for the random, and then coming to the random forest, I apply hyperparameter tuning, find the right parameters, tune the model again, fit and transform on the train and test data, test for overfitting, and evaluate their performances. For the LSTM, after I define the training and test data, I create lag sequences. These are basically 12 temporal lag sequences. So what it does is, on the feed, I'm using 12 sequences because I want to use historical data from the past 12 months to predict the future, like the upcoming the daily highest prices for the upcoming months. And that's what goes into the LSTM model's input. Then I define the total number of layers. Like, for example, how many predictions do I want to make? If I want to make predictions for the next 6 months, that means I need 6 plus 1, 7 layers, the current month, and 6 months from today, or from the current month. Then what I do is I define the LSTM model with early stopping. Now what this early stopping is, it'll also come into the next slide shortly, but I'll give a brief idea of what it is. So it finds the optimal number of epochs until which we run our LSTM model. So beyond which, what it says is, at this optimal number of epochs, the model will start overfitting. So we don't need to run after that, and it automatically stops. It uses a function of Keras called the early stopping, and the moment it finds the optimal number of epochs, the LSTM model stops over there. Then again the same thing, fit and transform on the train and test data, and evaluate their performances on some regression testing metrics. So coming back to the LSTM, to the to the LSTM early stopping. This In this graph you can see this is what early stopping does. So what I do is I define a certain number of maximum epochs until which I want to train my data, and the moment it sees that the validation loss and the training loss plateaus, it stops. That is our effective, or we can say the optimal number of epochs. It could be somewhere between 15 or 20, and if we use a value greater than this, then our model starts overfitting. So this is how this graph, training loss versus validation loss, helps us finding the epochs. This is like the hyperparameter tuning. And lastly, once both the models are deployed and they're tested on the, and they're fitted on the training data predicted on the test data, I use some regression testing metrics to gauge their performance. So I've used 3 regression testing metrics: the root mean square error, the mean absolute error, and the mean absolute percentage error. And you can see that the difference is large. The LSTM is way more superior than the random forest, and especially when it comes to the mean absolute percentage error, there is like a wild difference between them. LSTM has an 18% percentage error, whereas the random forest has around 428%, which is not a very good figure, and this was expected. Why? Because it's a general conception in data science that regression models do not perform well on time series data. This is something that I also wanted to test, and that's the reason why I chose random forest from the machine learning stack deliberately to perform it on the time series data. And I wanted to see to until what extent is this general perception true. And what I realized is that regression models are not suitable for time series analysis because they fail to capture the temporal aspects of the times of any time series data. Like for our like in our case, we have data from January 2019 to 2023. So random forest or any regression model for that instance will not be able to capture temporal instances. Like for any instance in between, it won't be able to take into consideration the data from the previous time step or like previous 12 time steps, and hence it won't be able to predict for the upcoming time steps like the next 6 months. LSTM on the other hand addresses this very issue. As you could see that uh, the lag sequence that we create, these very lag sequence are those temporal instances, and what it does is it creates a time series data based on these lag sequences. And when we define the number of output layers, it uses these lag sequences to predict the next few months, or like whatever, how many months or years you want to define. That depends upon your requirements. So this is the conclusion that I found why LSTM is the better model, and why regression models do not perform well on time series data in general. And also, like, get more insight into the overfitting, underfitting aspects, how to find the optimal number of epochs, hyperparameters, etc., so that we can have the best configurations of our best performing models and deploy it accordingly. So this is all about my project, and that is how I deployed it, how I tested it. I went through the entire data product life cycle. And and at this point I would like to end my presentation and express my thanks to everyone, especially Romeo Geisler, for coming up with this amazing this course structure. It was very nice, very insightful, and I got to learn a lot. Thank you so much, and have a good day, everyone.